In this session, I am going to talk about linking remote sensing with modeling. I encourage you after this presentation to come back and view episode 4 of the Geospatial Revolution. And this was a project that was an integrated public service media and outreach initiative, and it's all about the world of digital mapping and how it is changing the way we think, behave, and interact. It covers climate change, preventing hunger, tracking disease, and mapping power to the people. There's a link on this slide which you can find on Blackboard. So in this discussion, we'll cover marine remote sensing, hydrological models, terrestrial environments, atmospheric applications, world heritage, and briefly touch upon time series analysis. I'm going to start with marine remote sensing. So you can see here just a few of the areas that are benefiting from remote sensing and geospatial analysis when we look at the marine environment. So we have event-based mapping and things like weather, blooms of plankton, and events like oil spills benefit from remote sensing. Coastal features, in particular, looking at monitoring wetlands and estuaries and mangroves, tracking water quality, which can be determined by using remotely sensed images and looking at plankton quantities, pollution quantities, etc. The shape of the seafloor, which is bathymetry and rugosity. So bathymetry is maps of the seafloor heights or depths, and rugosity has to do with the bumpiness or the complexity of the seafloor. And the benthos is the bottom environment. So looking at all of these things as well as other biophysical properties are involved in remote sensing modeling. So remote sensing technologies identify parties potentially responsible for pollution. It can also help with minor spills before they cause widespread damage. And here's an example of the remote sensing bands and related instruments that were used recently for oil spill detection. This was from an article by Goodman in 1994. And you can see radar, passive microwave, different types of infrared, visual, and ultraviolet were used in this example. So here is an example of a visible image of the Exxon Valdez oil spill on the left, and you can see on the right the oil is absorbing solar radiation and emitting some part of it as thermal energy in the thermal infrared region from approximately 8 to 14 micrometers. And because oil has a lower emissivity or heat signature than water in the thermal infrared region, the oil has a distinctly different spectral signature in the thermal infrared region when you compare it with the background water. So UV scanners can capture the ultraviolet radiation that is reflected at the sea surface. So here's a diagram of a passive sensor, which is a UV sensor, and it's using the reflected sunlight in ultraviolet region from approximately 0.32 to 0.38 microns, and this is useful for oil spills. Again, oil has a stronger reflectivity than the water, so it stands out very nicely in this type of data set. And you can see here some of the mechanics of a rotating mirror, some scan motors, sensors, optics, etc. And then the instantaneous field of view is represented by the green arrow. By the blue circle within the green dotted arrow, which is the field of view. So again, the instantaneous field of view would be that blue cone representing the area on the ground that's being collected, and the field of view is where that instrument is rotating back and forth and collecting data along the path that you see as those blue lines measured as a scan width. So radar is an active sensor, and it operates in the radio wave region. Radar waves are reflected by the capillary waves on the ocean, and we can see bright images obtained for ocean water. Oil diminishes capillary waves as a result, and if oil is present in the ocean, then the reflectance is reduced. Therefore, the presence of oil can be detected as as the dark part in the bright image for the ocean. So here you can see a wavelength measured as a lambda from crest to crest. There's a pulse that is transmitted towards the sea, and then there's an echo that is scattered back towards the instrument. Knowing the physics of how fast that wavelength is moving, you can determine distance, and you can also be looking at the qualities of that oil spill detection. So an example of microwave application used for oil spill detection is to look at oil thickness measurements, and the oil emits a stronger microwave radiation than water, and it appears brighter than the water, which is dark in this background. So measuring oil thickness has to do with the interference of radiation from the upper and lower boundaries of the oil film. This is an example from the Archimedes 2 experiment, and the bright temperatures are increasing from light blue over the dark blues onto the reds and yellows, and the maximum brightness temperatures are 20 Kelvin on the left image and 17 Kelvin on the right image. So there's two types of radar, synthetic aperture radar, or SAR, and side-looking airborne radar, and they're the most common. SAR image is shown here, which was captured by RadarSat-1, and you can see the shoreline provides a similar impression as the oil slicks in the SAR image. The calm water also appears dark, which does give a false impression of oil. Here's the side-looking airborne radar being flown from a small aircraft, and it can detect spills over distances of more than 20 kilometers. Following a spill detection, the type and quantity of substances on the sea surface is analyzed at flight altitudes of approximately 300 meters. So you can see the arrows here showing the pulses that would be coming from the radar device, and the difference in the reflections that you would get from a clean sea surface versus an oil slick, represented by those blue arrows. So with side-looking airborne radar, here's an example of a ship that is seen as a white spot because of the high backscatter efficiency, and the ship is spilling oil, and that's the dark cloud below the ship, and the aircraft track is parallel to the left edge of the image, which explains the backscatter intensity loss from left to right with an increasing slant range. Here is an example of LiDAR, laser fluorescensor, and it's used to illuminate objects and detect and analyze signals which originate from that object as a result of the illumination. And so it resembles radar, but it uses ultraviolet, visible, or infrared region of the electromagnetic spectrum instead of microwave. And the pulse lasers are used as a light source. This one is showing you from a small aircraft, and since there's a high background radiation from sunlight in the UV, visible, and infrared during the day, this is sent out as a pulse, and daylight intensity is almost constant, and therefore the signals which originate from laser pulses illuminating an object can be easily discriminated from the sunlight-induced background. So LiDAR can be flown at any time of the day. Here's an example of a monitoring device, a video remote system on the coast. And the advantages of this is that it's non-intrusive, it can run automatically, and requires little maintenance. So it's standalone, and it consists of a video camera, which is in a weatherproof case. These are mounted on a tall structure, like this one is just showing a concrete and beam structure, and there's a mini computer wired to the camera and stored in a sheltered location with power and internet access. So here are some examples of things that you can monitor with coastal changes, and some of them are hazards. So we have rip currents that are shown in the upper left at the end of those red arrows, and they're the dark water. You can see beach cusps, the movement of those waves and sand patterns. In the lower left in C, you can see a straight sandbar, and then in image D on the right is a more complex sandbar. Coral reefs are a critical ecosystem for our ocean environments, and we are losing a lot of coral reefs for various reasons. The warming of the planet and global warming. There's also increased populations near shorelines, and so pollution and human interaction is also causing damage on coral reefs. And so in order to locate coral reefs, we can use bathymetric maps, and with remote sensing we can look at the kind of reef and its form, and scientists can try to find out which processes are active around the reef. And looking at bottom type classification, we can get information about reef communities and the surrounding areas, and habitat types, seagrasses, bare substrate, etc. And there's changes over time in the above elements. And remote sensing may be applied to track the evolution of human activities, which can negatively impact the coral reef environment. So for example, coastal urban centers, as they grow, they create more runoff in sewage and other kinds of pollution, and this can be very harmful to the coral reefs. And just interaction of humans themselves recreating on the beach or using it as a food source. When we talk about water quality, you can look at spatial coverage to include access to data and information about target sites that are inaccessible and or remote and hard to reach. You can monitor inland water bodies, including land surface water bodies and reservoirs. This can be challenging due to land adjacency effects and the need for atmospheric corrections that would be applicable in these environments. So some main topics are algal blooms, land use changes, vegetation growth, thermal spills, and nutrients. There are a lot of links in this presentation, and here's an example one here for the Environmental Protection Agency Science Inventory, and you are welcome to come back and explore an area that is of the most interest to you. Here is a decision support model, and so the NASA satellites are collecting the decision. A water utility analyst will log into a decision support system to view and then analyze that data by combining that data with in situ water quality, hydrology, and climate modeling data. You can run statistical algorithms to develop and test models, and then finally the analyst produces a water quality report for operations staff and managers to support decision making. Here is an example of water quality determinants. So we have a remote sensing image on the left, and you can see different aspects of a model shown as those GIS layers on the right stacked on top of each other, and you can look at sources of contamination, propagation, and life-sustaining environments for bacteria, and lake and residence factors. So all of these would be useful in the areas of agriculture, human and wildlife studies, climate, soil topography, and again, general water quality. So harmful algal blooms are a result of increased phytoplankton, and the way that we see those in a satellite image is through chlorophyll concentrations. Here's an example of the CWIF satellite, and it's showing the concentration of chlorophyll in milligrams per cubic meter, ranging from the lows in the blue colors 0 to 3, and then the highs would be 8 to 10 in the reds. And so harmful algal blooms can impact ecosystems. They can be toxic to a lot of organisms. They can also cause oxygen problems, drop in oxygen, and even dead zones. So here's an example of classifying the bottom type, which is the benthos, and you can compare the classification derived from an image. This one is from the CRIS onboard satellite proba, has a resolution of 18 meters, and the classification is from the hyperspectral data. So on the left image, it is an area in Indonesia, and it's showing you a classification map there with several different types of benthos, water, deep water, vegetation, different types of sand, different types of corals, seagrass, etc. And then on the right is another classification map made out of hyperspectral data, and again just showing you different classifications that have been put together by that analyst. And so can you find the noticeable difference between both classifications? Okay. Seafloor shape. So when we talk about bathymetry, that has to refer to the depth in the ocean, and then rugosity is a measure of complexity. And so on the left is a map of Navisau Island, and this is off of the coast of Haiti, and this is a bathymetric map that was created by NOAA and the Center for Coastal Fisheries and Habitat Research. So on the right is a side view of plotted in 3D of the different shapes that are found on a seafloor off the Navisau coast. And so you can see not only the general height, but also the bumpiness or the rugosity of this area. So satellite measurements give us a broad overview. They tell us how currents vary in time and space, but we also need data from other sources. So there are moorings, and instruments are attached to these moorings that stay in pretty much the same place if they're anchored, or they can drift with the current as floats. Sometimes they are mounted on buoys, flat platforms, or ships, and they are collecting oceanographic data that help us map currents in a model. So this is an example of a research vessel with a hull-fitted acoustic Doppler current profiler, and the GPS information is being sent. It's showing in upwards through the open water. At 2, we have our short-range acoustic Doppler current profile collecting information on the bottom, and then in 3 it's showing you that there would be an acoustic beacon which is actually attached to the seafloor. And by knowing the physics of sound propagation, we can measure water currents and record and monitor velocity of currents to generate a wave profile. So current meters are moored to buoys to measure the flow and direction of water past the sensor. A moored float can also be used for fixed sonar pulses and to record local conditions, and they can provide high quality long-term data about currents. So common applications include boundary currents and eddy systems. Surface buoys do have a disadvantage that they are very vulnerable to ships and surface weather that can damage or disrupt the buoy. And deep areas are places where we require high detail, and long-term data sets benefit from these types of surface buoys. Here's an example of satellite altimetry, and this is Envisat and JASON satellites on the CNES Poseidon 3 altimeter and RA2. And so they work by transmitting a pulse of microwaves toward the Earth's surface and then measuring the time it takes for the pulse to return. And this data allows us to get maps of the ocean height and also speed and direction of currents. So here are 2 maps showing spring and autumn sea surface heights and the variations. Okay, moving on to hydrological models. So here's a schematic of the hydrological model, and water is always in flux, as is energy from the sun. And this illustrates the major water and energy fluxes simulated in a project called SHIELS, the simulator for hydrology and energy exchange at the land surface. Again, there is a link there. If you are interested in any of these models, please come back and explore them in further detail. Here's an example of estimating the fractional water content by volume. And you can see this is a three-dimensional profile of showing moisture and temperature modeling, and it has vertical and horizontal grid configuration. And so soil moisture is estimated for each layer below the surface. And this is useful for looking at different aspects of hydrology and agriculture, among others. Here's an example of surface routing and stream flow. And so this is an event, a weather system, and you can see in the upper left the light green area is a polygon showing the most impacted areas. Then in the middle is the map output of the rainfall accumulations as estimated with satellite imagery, and then on the right is an aerial photograph of a flooded area. So with surface routing and stream flow, you can see here this is a graph of day of the year on the x-axis versus discharge, and the arrows are pointing to observed flood, an improved forecast, and then an actual operational forecast. So all of these components of remote sensing and ground in situ data and weather forecasting models are input into something like mitigating a flood. So this is an example of future forecasting and doing the best we can to see what conditions might be like in the future based on models. And this is a MODIS-based land surface temperature and looking at evapotranspiration estimation. So evapotranspiration has to do with the amount of water that's processed by vegetation in a certain area of the world, and by estimating this, we can look at ecological processes, things like world agriculture estimates, etc. Here is an example of the National Weather Service flood forecasting, and again, very useful for helping to protect lives of citizens that may be in the path of danger. An example of microwave brightness and soil moisture. So here we have a graph of volumetric water content that is graphed against brightness temperature. And this model is used to convert measured or modeled soil moisture and temperature conditions to microwave brightness temperatures, and for the purpose of validating remote sensing observations. So here are some soil moisture applications and algorithms. And so we have in the upper left aircraft and in situ data are combined into a land surface hydro model. We have soil temperature and moisture profiles. Coming up from the bottom, we also have what we're all familiar with now as the GIS layers of soils, vegetation, and topography, and these can be put in to represent input uncertainty. Then we get a radio brightness model, and we have brightness temperatures, and then finally on the right we've got some model outputs that are statistically rigorous, and they can be used to look at soil conditions. Moving on to terrestrial environments. So you can see here, these are some of the common terrestrial applications. Topography is the layout of the land. Measuring snow and ice is very important with climate change, and looking at water available for an area during the year related to the amount of snowpack. We have vegetation structure and chemistry, which is useful for ecological studies and agriculture. We already talked about soil. Again, very important not only for ecologists but for agricultural applications. We have riparian vegetation, surface properties, and composition and cover in the center, and then finally fire analysis. Here is an example of looking at tree heights in Costa Rica, and trees are important for estimating nitrogen storage properties, and so you can see here that this map is emphasizing the topography of this western part of Costa Rica. This is imagery that was collected on the Grand Prix fire in October 2003. This was the Aster sensor, and it was rendering color in the near infrared and the mid-wave infrared spectral regions. And the smoke emitted by the fire is nearly transparent in the mid-wave infrared image. But then on the left, you can clearly see those smoke plumes. You can create a model to look at the frequency of burns in an area and determine where there's a higher fire frequency versus a lower fire frequency, as shown here in this area of South Africa. Looking at tsunami assessment, this is digital globe QuickBird imagery related to the 2004 Indian Ocean earthquake, and it was taken before and after the tsunami. ENVI software was used to process the areas that were changed by the tsunami, giving rapid measurement of the affected area and automatically delineating those regions from areas that were unaffected by the tsunami. This is an example of urban expansion in Sydney, Australia. So looking at change over time, you can track the increased expansion of the urban areas that you can see in this image. So with population expansion, maps like these showing cities with more than 1 million people are useful, and you can see quite a dramatic difference between the cities that have more than 1 million people in 1900 and the cities with more than 1 million people in 2015. There are several tools that are developed by different entities. This is a riparian mapping tool, and it inputs a DEM, a NAIP imagery, Landsat TM, Spot 5, image segments, and training data in order to look at the riparian or the river extent and composition output. This is an example of land cover. This is water and land cover conditions in Lake Chad, Africa, between 1972 and 2001. It's pretty easy to see that drought is affecting this area. So land use in geography means the usage of land by humans. It's a variation or change of land use, for example, forest clearances, growth of cities, and also renaturation of former industrial sites back to more ecological areas. Here's an example of vegetation structure and chemistry, and ecosynth procedure for vegetation measurement using computer vision. So we have our image acquisition, then on the moving over to the right is a mosaic, and then moving on to an automated feature recognition, bundling that adjustment, geo-correcting it, and then finally getting a canopy and terrain filtering model, which is showing vegetation heights. Here is agronomic insight from imagery and comparing topography, crop surface map, a relative biomass, and then an NDVI, which is greenness overlay on that biomass, an orthomosaic on the biomass, and then finally a map output, which is representing the model. It's possible to integrate LiDAR and Landsat to estimate forest regrowth. So this is showing a successional series of observed versus predicted canopy cover measured in percents. So when we look at snow and ice, every surface with a temperature greater than absolute zero emits some form of electromagnetic radiation. So some satellite sensors detect visible light reflected from an Earth's surface or atmosphere, and others detect radiation emitted from the Earth. Sea ice is measured using visible, infrared, and microwave energies. So after a model is run, the output is a set of sea ice variables that are relevant to studying, such as concentration of the sea ice, extent of coverage, and thickness. And over time, these are all input into known grid cells, which are geographic locations, and model outputs can be evaluated using sea ice observations to determine how accurate the model is. So this one is showing external forcing, and then there's dynamics, horizontal transport, thermodynamics, redistribution, and then finally the output. So how they work is that there are numerical models that represent how much sea ice is in cells. A cell is the smallest discrete area that can be described by the model. Within each cell, there's no variability in space of any of the properties. Each cell describes several dynamic and thermodynamic properties, such as thickness, temperature, and velocity. The entire group of cells is referred to as a domain, and as the number of grid cells increases, so does the spatial resolution. Having a larger number of grid cells will describe sea ice conditions at smaller scales. So larger number of grid cells, you could get down to tens of kilometers versus hundreds of kilometers. The limitation is the cost of storing and computing the model does increase substantially with your increase in the grid cells. So here's an example from the National Snow and Ice Data Center. This is a sea ice index. You can see on the left that there's two tabs possible. On the top, monthly or daily reports or composites, and then at the bottom you can look at extent, concentration, anomalies, and trends. And so the graph on the right is showing the relative amounts of sea ice in the northern hemisphere, and it's pretty obvious to see that that is a negative slope, meaning that overall the trend is a decrease in sea ice. So we're going to move on to atmospheric applications, and we can look at things like top of the atmosphere irradiance, surface irradiance, and so it's very different because there are many gases, clouds, and other factors that sun's energy is going to interact with between top of the atmosphere and the surface of the earth. We have emitted long wave, the study of gases and aerosols, atmospheric properties, cloud properties, and rainfall. So when we think about top of the atmosphere versus the Earth's surface, and we look at emitted long wave, there is energy from the Earth atmosphere. Over time, there's flux, which strikes the detector area and becomes irradiance. This is measured at a given wavelength interval, and we have monochromatic irradiance over a solid angle of the Earth. And this is the radiance observed by the satellite radiometer. This is described by the Planck function of how light moves through our atmosphere, and this can be inverted to brightness temperature. There are two IGEC concept modules on top of the atmosphere, and you can come back and review those if you are interested in this type of modeling. With gases and aerosols, aerosols use the signature of aerosol scattering, and trace gases use the signature of gas absorption. So those are the spectral signatures that are used to study pollutions, direct radiative forcing, indirect radiative forcing, etc. So every trace gas has its own unique absorption spectra, which are represented here by these graphs. And you can see that there are troughs and peaks, and the troughs are windows of absorption. So with trace gases, satellites detect backscattered solar radiation and or emitted thermal radiation. Trace gases absorb radiation at specific wavelengths. A model is used to derive a trace gas column concentration or column amount. There's limitations because the sensor may not be sensitive to the spatial or to the variation due to spatial resolution, spectral limits, clouds, limited sensitivity in the vertical column of the atmosphere, and lack of data for validation. But we do know trace gas concentrations vary throughout the atmosphere. This is important for meteorology or transport studies, the general chemistry of our Earth, day versus night comparisons, and polluted versus non-polluted regions. Here's an example of some trace gas measurements from space, just a few that are available: ozone, tropospheric, and atmospheric applications. And these are the primary sensors that are monitoring aerosols in our atmosphere. We have MODIS, VIIRS, MISR, and OMI. Here's an example of looking at the optical thickness of ice clouds on the left, and on the right is looking at image from a polar orbiting satellite to monitor cloud amounts over the Great Lakes region. So a schematic of the modeling. So we have an ice particle model represented by the cloud in the middle. You can see that there's several components: in situ measurements, microphysics, a scattering model, generalized circulatory models of the Earth, and satellite remote sensing. And so the arrows are showing you the contributions and the many different components involved in monitoring ice clouds. Here's an analysis of field inventories for a National Forest Carbon Monitoring Project. So looking at the processing of CO2 on our planet, it's important to look at the carbon that is stored in vegetation and how that is going to vary with things like deforestation and urban expansion. So here's an example of using remote sensing to look at volcanoes. It's very effective for measuring ash height, and this is an ash plume from an Icelandic volcano. After a century of declining rainfall, there's major changes in the forest structure and photosynthesis in Hawaii. Here's an example showing you data of the leeward versus the windward side of the island. And then World Heritage. So cultural heritage is a legacy of physical artifacts and intangible attributes of a group or society that are inherited from past generations. It's maintained in the present and bestowed for the benefit of future generations. But often what's considered cultural heritage by one generation may not be accepted by the next generation. Then it can be reviewed by a succeeding generation and constitute a fundamental part of the identity. So it's important to document or to access remote sensing data that we have on monuments, groups of buildings, and historical sites, for example. And then just briefly, a time series analysis. We want to understand or improve our understanding of the data generated mechanism, fit a model to the time series, forecast or model the time series, and possibly control or influence the time series. So with time series, we aim to identify the nature of the phenomenon, and this is represented by a sequence of observations, and then forecast or predict future values. In order to do this, we need to identify a pattern of observed time series data, express this pattern in mathematical terms, interpret the pattern in light of other data or possible theories, and then integrate it with the other data to refine and develop those theories. So here's some examples: plant phenology, vegetation. There is also sea ice in the Arctic, and the phytoplankton blooms. So these are all tutorials that are available to you if your work as a remote sensor is going to involve any of these topics, or if you are just curious to see the procedure, please explore these tutorials. So in conclusion, what you need for a model: you need products and raw data, and these are handled by the computer with algorithms. You need a place to store your models or data archives. You need web tools to share your models, and you also need standalone tools often to process various aspects of your model. So you can see here, this is a combination of Rector and Vaster Vector and raster data, we have points of interest, streets, parcels, elevation, and land usage, which are overlain on a complex Earth. And this concludes remote sensing applications. Thank you.